So we're going to talk about effective nuclear charge. So Coulomb's law states that is talking about the attraction between the negative electrons and positive protons in the nucleus. And that depends on, one, the magnitude of the nuclear charge. For example, +3 or +1 would be different magnitudes. And two, the distance between them. So if the electrons and protons were close to each other, then the attraction would be strong. While if they were further away, then the attraction would be weaker. The equation is F equals Coulomb's constant times Q1 times Q2, which is the charges, divided by the distance between particles squared. And so when there's only one electron in the atom, like a hydrogen atom, then this attraction is very strong. So hydrogen atom, this is the nucleus. This is that one electron. This nuclear charge is very strong. The single force acting on the electron comes from the nucleus and is called nuclear charge. However, when there are other electrons in the atom, an extra repulsion force, so because both electrons are negative, so then there is repulsion, which weakens the nuclear charge, or the attraction. And then you add more electrons, more repulsion. Okay. And this phenomenon of where the electrons cause an extra repulsion and interferes with the nuclear charge is called the screening or shielding effect. Screening or shielding effect. So over here we have, so effective nuclear charge is the partially screened nuclear charge. So this is the equation: net attraction equals Z, which is the nuclear attraction or number of protons, minus S, the screening constant, or also known as electron-electron repulsion. And to simplify, this is ZF, which is Z effective, equals Z minus S. And that is a very common equation you'll see. Z effective equals the nuclear charge minus the number of inner electrons. So electrons other than valence electrons, and that's what we call those core electrons or shielding electrons. So now let's talk about Slater's rule. So Slater's rule, again, we have the equation Z effective equals Z minus S. So Slater's rule is basically saying when the N is so complicated, but it's like 0 to S, 0.35 to S, 0.85 to S, and 1 to S, and you'll most likely be given the numbers. So basically, how you'd use it, an example of using Slater's rule is finding the effective nuclear charge of phosphorus. So it's better, Slater's rule is really complicated, so it's easier to just learn about it through example. Again, I'll just write out the numbers. It's 0, 0.35, 0.85, and 1. Okay, so phosphorus, if you look on the periodic table, has an electron configuration 1s2, 2s2, 2p6, 3s2, 3p3. Okay, so we are going to find, right, we have the equation Z effective, which we're trying to find, is Z minus S. So first we'll find Z, and how we do that is just the number of protons. So if you look at the periodic table, it's 15. You can also check with the number of electrons here. 2, 4, 10, 11, 12, 13, 14, 15. Okay, so we have 15 protons. So I'll just write atomic number. So this is how we find Z. And now we're going to find S, which is a lot more complicated. So if we go, so N equals 3, N equals 2, N equals 1. So the third level is 3s2, 3p3. So that would be 5 electrons in the third level. However, we have to subtract 1 to get 4. And we subtract 1 because N equals 3 has our electron of interest, and we don't include the electron of interest. So we subtract 1 to get 4. So we're going to write 4 times 0.35. And then, I know you're probably confused right now. It'll start making more sense. N equals 2. We have 2s2, 2p6. So we have 2 plus 6 electrons in the N equals 2 orbital. So that's 8. So 8 electrons. And here, we don't need to get rid of the electron of interest. So we'll just do 8 times 0.85 plus N equals 1. How many electrons are in here? Just 2. So we write 2. And we write here 2 times 1. And what you'll get after, let's see, is you'll get 10.2 as your S. So the effective is simply Z minus S, which is 15, minus 10.2, which is 4.8, which is your Z effective. Okay, so that is using Slater's rule. Now we're going to talk about periodic trends of Z effective. So the effective nuclear charge increases, or generally increases, from left to right. And that is because the number of protons as you go from left to right on a periodic table increases. So Z effective increases. So again, we're still talking about effective. Effective nuclear charge increases from left to right because the number of protons increase, and the increased number of electrons are valence electrons and thus screen ineffectively. So now we're going to talk about columns. When you go down a column, this is slightly, so this is less. But as you move down columns, the effective nuclear charge decreases slightly, or so the nicer we get. Because electron density, and so the core electron cloud is less able to screen valence electrons. So again, so the main thing you have to memorize is because the number of protons are increasing, that's why as you go right, it's increasing. Okay, hold on, I just want to check something. Okay, let's just continue. We're going to continue now to atomic radii. All right, yes, a slight but it's definitely more as you go across. So it increases as you go down just a little bit. Okay, atomic radii. So an atomic radius cannot be directly determined due to the uncertainty in the position of electrons. So how do you find the radius of an atom if you don't have a defined parameter? The bonding atomic radius is the radius of an atom when it's bonded to another atom. So pretty self-explanatory, bonding atomic radius. And so it's when it's bonded to another atom. So it is to calculate the distance between the nuclei of two atoms in a bond divided by 2. And for non-bonding atomic radius is the radius of an atom when it is not bonded to another atom. So it is calculated as the closest distance between the nuclei of the two atoms in a collision divided by 2. So again, bonding radius is half of the bond distance, and non-bonding radius is half of the diameter. So radius equals bonding distance divided by 2, and for another one is for non-bonding is radius equals diameter divided by 2. And since non-bonding is not bonding, the non-bonding atomic radius is always bigger than the bonding atomic radius. So again, bonding, so that means bonding radius is always smaller than the non-bonding radius. And now how to estimate bond lengths. So estimating bond lengths, you take radius of element 1 plus radius of element 2. So an example is finding the atomic radius of carbon and sulfur. Yeah, so let's find this example problem, bond length of carbon and sulfur. So what is the atomic radius of carbon? I'll tell you, it's 0.76 angstroms. And what is the atomic radius of sulfur? That is 0.31 angstrom. So the answer you get 1.07 angstrom. Or no? So yeah. So again, you find that you just add the two atomic radiuses. Okay, so let's talk about the trend on a periodic table. So generally, atomic radius increases as you move left, and generally atomic radius increases as you move down. So let me show you what that looks like. Atomic radius, as you go down, and this is more important, so this would override the other one. As you move down, the number of sublevels increase, so of course it'll also increase. And atomic radius increases this way. And this is because, as you remember here, as you go that way, the number of protons increase. And when protons increase, the attraction increases. And when the attraction increases, it gets pulled in a bit. So it's biggest over here. Beryllium and boron are adjacent in the same period. The atomic radius, however, of boron is smaller than that of beryllium. This is because the number of protons is greater, which increases the valence electron attraction to the nucleus. So this will be beryllium here and boron here. Now let's talk. Hydrogen and lithium are adjacent in the same group. The atomic radius of hydrogen is smaller than that of lithium. This is because the energy level of valence electrons is greater, which increases the repulsion between the valence electrons and electrons in the lower energy levels. So this higher energy level also means that the valence electrons are more likely to be found further away from the nucleus. So exceptions. There are no exceptions when moving down a group. When you move down, it will increase because you're adding another sublevel, so each time it increases. But there are exceptions horizontally. And so noble gases tend to be bigger than the halogens in their period, except for helium and krypton. So copper and silver are bigger than the transition metals before them due to the way their valence electrons behave. Tellurium is smaller than iodine, which is equal to size in antimony. But the main thing is noble gases tend to be bigger than halogens, which contradicts this thing here because you have noble gases here and halogens here. And these are bigger, even though based on this horizontal trend, it seems like halogens should. So let's do some practice problems on atomic radius. So order the following elements in order of the size from smallest to largest radius. So oxygen, phosphorus, chlorine, sulfur. That marker is great. Okay. OPFS. So let's take out our periodic table and see where oxygen, phosphorus, sulfur, chlorine. Okay. So take a minute to get your answer. Oh, sorry that took so long. I cannot find phosphorus for a sec. Okay, so this would be from biggest to smallest. If you want smallest to biggest, it would be FOSP. So I did biggest to smallest. Okay, second practice problem. Using the information in the table, estimate the bond length between oxygen and hydrogen in an OH molecule in PM. So remember, bond length is just adding the two bonding radiuses. So for oxygen, I'll just tell you, the bond length is 0.66 angstroms, plus hydrogen, which is 0.31 angstroms, which is 0.97 angstroms. And now we want to convert it into picometers. And the conversion is 1 angstrom equals 100 picometers, so that just equals 97 picometers. And that is the answer. The third practice problem: which two of the following elements will have the longest bond between them if they form a molecule? Lithium, phosphorus, calcium, and fluorine. So which two of the following elements will have the longest bond? So the first step is finding which one is the largest. So lithium is over here on the periodic table, so that's the largest. And they're all in n equals 2 or n equals 1. And then next, phosphorus is the biggest because it's also n equals 2. And so lithium and phosphorus would create the biggest bond length because they're the biggest bond. Okay, now we're going to talk about ionic radius. So, factors that determine the size of an ion, they are very similar to the factors that determine the size of an atom. So there's the nuclear charge, the number of electrons, and the n level. So more electrons means a higher radius or greater radius because there are more electron-to-electron repulsion, causing the valence electrons to spread out. Higher n value means a larger radius because the valence shell is further from the nucleus. Remember, as we went down, because there are more levels, the ionic radius or the radius increased. And higher nuclear charge means a smaller radius because there's more attraction between the protons, create stronger positive attraction to nucleus, pulling the electrons in towards the nucleus. And for Z effective, the more accurate way of describing the nucleus effect on the electrons, a larger Z effective means smaller radius because the electrons are pulled into the nucleus more. Okay, so now let's talk about the main thing that determines ionic radius. Anions, which are negative, and cations, which are positive. Big, small. So anions have more electrons. For example, Cl minus has one more electron than protons. So more electrons means bigger radius. So the ionic radius would be bigger for anions. And then opposite for cations. So anions have larger radii than their neutral element. They'll state, and cations have smaller radii than their neutral elemental state. And why? I already explained briefly, but cations have fewer electrons, so less electron-electron repulsion and less shielding. And so thus the Z effective increases, which means the radius decreases. Anions have more electrons, so more electron-to-electron repulsion and more shielding, which means Z effective decreases, so that means radius increases. So which of the following impacts the size of cations or anions? All of the above, all three. Z effective, number of electrons, and higher or lower n values. So the trend, as one goes down a group of the periodic table, ionic radius generally increases. Increases. So as you go down a periodic table, ionic radius increases. Well, the main thing you should remember is cations versus anions. So which has the larger radius, Li plus or K plus? Then we'll look which one's further down. Potassium is. And now bromine, Br minus or Fr minus. the larger radius is bromine. And as you go across the period side, generally decreases because of the higher nuclear charge. So, again, very similar to atomic radius. And let's talk a little about the U shape. So the U shape is increasing, so it's like a graph. So atomic number increasing and radius. So right, as you increase the atomic number, you expect the radius to go down, right? Because the effect is getting greater, so bigger attraction, pulling in the electron. But then it does a little U and goes up a bit. Like that. Okay, now let's talk about the isoelectric series. So U shape, that's the U shape. Now let's talk about isoelectric series. Isoelectric series. This is when there are the same number of electrons. Same number of electrons, but the number of protons increases. So there are different elements with the same number of electrons. Different elements with the same number of electrons. So for example, O2 minus, F minus, Na plus, Mg2 plus, Al3 plus, all different elements, but they have the same number of electrons. So, what is the trend of the ionic radius? So remember, when it's negative, when it's an anion, is greater, so it's decreasing. The ionic radius is decreasing. Okay, now let's talk about ionization energy. So ionization energy is the energy needed to remove an electron from an atom. So the minimum energy that needs to get absorbed to remove an electron. And since energy is being absorbed, that means it's negative because you're absorbing energy. We'll talk more about that later and how electron affinity is the opposite. So the first ionization energy is the energy needed to remove the first electron from neutral atom. The second ionization energy is the energy needed to remove the second electron from neutral atom. The third ionization energy will be third, so on. And so since it gets harder and harder to remove an electron, first ionization energy is always, third ionization will be greater than the second ionization, would be greater than the first ionization energy. So what would have a greater ionization energy? The first ionization energy or second ionization energy of sodium? And the answer would be, no matter what element, it will always be the second ionization energy over the first one. So periodic trends in ionization energy. So as you go across a period, the number of protons increase, which means the ionization energy will also increase because the ionization energy is the amount of energy needed to remove an electron. So if the Z effective is increasing, if the attraction is increasing, that means it's harder to remove the electron. If it's harder to remove an electron, you need more energy to remove that electron. And then as you go down, it decreases because we already learned that when the atomic radius gets bigger, the attraction is weaker, so it's easier to remove the electron. So this is the trend for ionization energy. Increases. So the smaller it is, the harder it is to remove an electron, which means you need more energy to remove that electron. So higher ionization energy. So of course there are exceptions to the trend. For example, beryllium and boron, and nitrogen and oxygen. And this is because of the repulsion of paired electrons. So it's having ionization energy generally increases, but beryllium and boron and nitrogen and oxygen are exceptions. So what would have a greater ionization energy, cesium or zinc? And the answer would be zinc, because cesium is around here, like over here, and zinc is closer to this spot, so higher ionization energy. So let's see. So let's talk about the electron configuration of ions. So what will be the electron configuration of tin if 4 electrons are removed? So tin and then you write the electron configuration to make it shorter. I'll do the noble gas one, 5s2, 4d10, 5p2. So tin, if 4 electrons are removed, so if it's SN neutral at first, but when you remove phase, making cation. I got my other video to play. Sorry about that. Okay. So 31, for example, the total is 112, then you do like the 31 relative abundance over 112 times the mass, and then plus for each one. Alright, so now let's talk about fragmentation. Fragmentation occurs as the process of ionization breaks apart large molecules. So when a sample of a pure compound is analyzed in the mass spectrometer, some of the molecules get ionized whole, while some molecules are fragmented and broken into pieces. So, question, given the mass spectrometer of benzene, match the fragmented ions to each of the letter P clusters. So, this one, I'll let you see the problem, and you can try to figure it out. So, cluster A over here, cluster A. So each cluster corresponds to an ion. It's like each ion has a mini mass spectrum in the entire mass spectrum. So it's based on mass. Cluster A has an average atomic mass of slightly less than 15 AMU. So it says here 15 AMU. Which corresponds to CH plus. Because the atomic mass of around 12 plus 1 is about 13 AMU. And then the cluster B has an average atomic mass of around 25 AMU, corresponding to C2H2 plus, because the atomic mass of C2H2 plus would be 2 times 12.01 plus 1.01, which is about 26 AMU. So you do that for each, and so again, you get the numbers. So for A, it says 15 here, and so you want which one has an atomic mass of about 15, which in this case is 12.1 plus 1.01. Alright. And so if there is an average atomic mass of 40.08 for calcium, then the most common isotope of calcium is 40, Ca40, because it's so close to 40. The last one we're going to talk about, or second to last one, is electron affinity. Electron affinity is the energy change that occurs when an atom gains an electron. It measures the attraction or affinity of the atom for the electron. So electron affinity, because it is accompanied by an energy change, gives values in terms of kilojoules per mole. In addition, because energy is released when an electron is added, the reaction is exothermic, which means the sign of most electron affinities is negative. So again, it's most. You'll see later that halogens are actually positive. So in ionization energy, we learned that it's always positive because it's absorbing energy. But in electron affinity,